Hi friends, we are going to discuss the additive manufacturing technologies. My name is Tusharkumar Gharge. Uh, Now we are going to discuss laser engineered net shaping and electron beam melting. Hmm, Now, what is lens? Lens, also known as laser powder forming, is an additive manufacturing technology developed for fabricating metal parts from a computer-aided design model by using a metal powder injected into a molten pool created by a focused high-powered beam. The strength of these technology lies in their ability to fabricate fully dense metal parts and tooling with good mechanical properties at a reasonable speed. Now this is a schematic diagram of the laser engineered net shipping. Here it shows the nozzle feeds the metal powder into the substrate, and laser beam melts the powder. In this way the part is fabricated in layer by layer fashion. Now how lens works. A high power laser is used to melt metal powder supplied coaxially to the focus of the laser beam through the deposition head. The laser beam typically travels through the center of the head and is focused to a small spot by one or more lenses. The excitable is used to move in a raster fashion to fabricate each layer of the object. Now, the laser beam may be delivered to the work by a simple right angle mirror. Metal powders are supplied and distributed around the circumference of the head either by gravity or by using an inert pressurized carrier gas. An inert gas is typically used to shield the melt pool from atmospheric oxygen for better control of properties and to promote layer by layer adhesion by providing better surface wetting. Now, the build volume is usually contained within a chamber to the isolate process from ambient surrounding and to shield the operators from possible exposure to fine powders and laser beam. The laser power used varies greatly from a few hundred watts to 20 kilowatts or more, depending on the particular material, feed rate, and other parameters. This is the working diagram of the lens system. Here it shows the powder material supply carrier gas. There is upside laser supply and the mirror to guide the laser beam. Then there is a lens to focus the beam. Then there is a stout gas inlet, and there is a metal deposition head, and at last there is a XY table. Now the capabilities of the lens system, the ability to build fully dense shape, it is the main capability of the lens system. Closed loop control of process for accurate part fabrication, ability to tailor deposition parameters to feature size for speed, accuracy, and property control, composite and functionally graded material deposition, 3 and 4 axis systems for complex part fabrication. Materials used in lens system are stainless steel, inconel, copper, aluminum, etc. Reactive materials such as titanium are also used in particular areas of interest. Alloys of stainless steel, tool steel alloys, nickel-based alloys, and the titanium alloys also used, as well as composite and functional grade material also nowadays are used. Feedstock used in lenses are in powder feedstock, but there has also been work done with material provided in the form of wire. Material is fed off axis to the beam. Using powders, material composition can be changed dynamically and continuously, leading to objects with properties that might be mutually exclusive using classical fabrication methods. Advantages of lens system: near net shape parts can be produced when it is not possible to make an item to exact specifications with good metallurgical properties. In case of post-production, light machining, surface finishing, or heat treatment may be applied to achieve end compliance. Large parts can be manufactured tools and fairly quickly in good selection of metals. Repair and recondition of expensive items such as jet engine components originally made by conventional production techniques. Opportunity to reduce the time and cost required to functional metal parts. As a material additive process, additional cost savings will be realized through increased material utilization as compared to bulk removal process. Disadvantages of less. Machinery is big and expensive and it uses a lot of power. Overhangs and undercuts may require support structures that will need substantial secondary machining to remove them. Hence, anything fabricated by the technology will require at least some final machining and finishing. Application. Fabrication and repair of injection molding parts. Fabrication of parts that made from titanium and other exotic parts for aerospace applications. These applications does not emphasize on support structure for overhanging sections. These are the components produced by the lens system. Now we are going to discuss the electron beam melting system. This is the working diagram of the electron beam melting system. Here it shows the parts: high voltage cable, bias curve, primary anode, electron beam, focusing coil, deflection coil, weld bead, prism, telescope or weaving. Electron beam technology manufactures parts by melting powder layer by layer with an electron beam in a high vacuum. In the electron beam melting process, fully dense metal parts uh, are built up layer by layer of metal powder melted by powerful electron beam. Each layer is melted to the exact geometry defined by the CAD model. This process is also similar to the laser engineered net shaping, but here the electron beam is used. The electron beam melting process takes place in high vacuum and high temperature, resulting in stress relieved components with material properties better than cast and comparable to rough material. The vacuum system provides a base pressure of 1 into 10 to the power of 5 millibar or better throughout the entire build cycle. During the actual melting process, the partial pressure of helium is introduced to 2 into 10 to the power of 3 millibar. This clean and controlled build environment is important to maintain the chemical specification of the build material. For each layer in the build, the electron beam hits the entire power bed to an optimal ambient temperature specific for the material used. Electron beam melting requires support structure, build anchor parts, and overhanging structure to build to the platform. This enables the heat transfer away from where the powder is melted. As a result of all these above, the parts produced with the EBM process are free from residual stresses and have a microstructure free from the martensitic structure. This is the schematic diagram of the EBM system. At the top here it is the filament, anode and the high voltage which produces the electron beam. Now there of below focusing coil, deflection coils are there. Deflection coils deflect the electron beam as per the CAD model. Process description of the electron beam melting system. The EBM machine reads the data from 3D CAD model and lays down successive layers of powder material. A thin layer of metal powder is selectively melted by a computer-controlled electron beam. The parts are built up layer by layer. The machine distributes a layer of metal powder onto a platform which is melted by an electron beam. The build platform is then lowered and the next layer of metal powder will be coated on top. The process of coating powder and melting where needed is repeated and the parts are built up layer by layer. Electron beam may have a characteristic length of tens of microns to mm depending on the degree of focusing of the beam. The electron beam is operated in pulse mode. This is achieved by appropriately biasing the biased grid located just after the cathode. Increasing the beam current directly increases the energy per pulse. High energy pulses in excess of 100 joules per second can machine larger holes on thicker plates. A higher energy density, that is for a lower spot size, The material removal would be faster through the size of the hole would be smaller. The plane of focusing would be on the surface of the workpiece or just below the surface of the workpiece. Advantages of EBM system. Parts can be manufactured in some standard metals with high density by electron beam melting. A good mechanical properties can be obtained by EBM system as compared to traditional production technologies. As compared to laser melting, electron beam produces less thermal stress in parts and therefore requires less support structure. Electron beam melting is still a slow and expensive process that only works with limited set of metals. Parts usually require quite a lot of post-processing. As compared to laser melting, the technology does not achieve equally good surface finishes. Applications of electron beam system: small series parts down to one of a kind are produced directly by electron beam melting. Prototypes are produced for form or fit and functional testing. Support parts such as jigs, fixtures, heads are produced directly by EBM. Holes can be drilled in thin plates or thin sheets using a single pulse, but thicker plates uses multiple pulses would be required. These are the components made by the EBM process. Thank you.